power is helping businesses to enable data analytics through semantic modeling. My colleague and me today are going to give you a first glance on what NetLume is, where it came from, and how it does what it does. We'll be starting off with a little bit of background about ourselves and about Idatase, and we'll then straight dive into a demonstrator of NetLume, so you can already get an idea of how it looks and what it does, and we'll then continue with discussing a little bit the problem it's solving and its business and technological applications. Before we wrap up, and before we give you the chance to get your questions answered, we will wrap up with a couple of key points. Now, so let's get started. First, a little bit about us. My name is Paul. I'm the CTO and co-founder of Idatase, and I'm coming from a rather technical background with a couple of years of experience in full stack development, but I have moved since to a more data science kind of perspective on things. Today I'm leading the technical product development team at Idatase, and yeah, that's so much about me. I'm not alone here today. I'm with my colleague Karl-Heinz, who wanted to say one or two words about himself, but it seems he's muted in this call. So let's see if we can unmute him. Otherwise, I will quickly give him an introduction. Okay, sorry for the delay. Seems like that it's not able to be unmuted, so I'll give him a quick introduction. But then it's also going to be quite difficult for him to speak at all. Anyways, Karl-Heinz is the CTO and co-founder of Idatase, so as well from a technical perspective, although he likes to say that he's more trying to work on the things that are rather impossible or seem impossible. So in that sense, he also followed his passion and studied computer science with a focus on artificial intelligence and machine learning. Has there also had several publications in brain-computer interfacing and is doing still interesting research there. Now he's leading the technical innovation group at Idatase and is mainly responsible for getting the right and the most interesting ideas and how to use them. Now, so much about Idatase, about us two. But what about Idatase? Who are we actually working for or with? Now, Idatase started as a consultancy in 2014 with a strong focus on the energy sector, specifically delivering data analytics solutions to businesses in the energy and utility sector. What started as a consultancy quickly turned ways, though. If you look already in 2015, we see that there was a change in Idatase's path. And that change basically came from seeing one and the same thing over and over again in as many projects as Idatase implemented. There was a constant struggle between businesses and internal businesses, between the data scientists and the domain expert of these businesses. While implementing analytic solutions, they were constantly struggling with finding the right basis of talking to each other. This language gap between those two groups resulted then in really fragmented approaches to analytics and specifically also IoT approaches and to rather slow adoption of these solutions. Idatase came up with a solution for the problem, NetLume. And since 2017 now, Idatase is solely focused on delivering NetLume to the world. So now Karl-Heinz seems to be also part of the microphone owning.
Yes.
Now, as I said, we wanted to straight dive into a demo in order to show you right away how NetLume looks and what it does, and so you can basically get an idea of what it offers in order to see what the problem is and how it's being solved. For this demo, we will go ahead and we will pretend to be the owner of a wind park and the operator of a wind park. And the idea is that we have noticed that we get a lot of data from our systems of our turbines and wind parks. And we want to see what we can do with this data, and we want to see whether we can generate interesting information that could help us work better and faster or more efficient even. So we've been given NetLume, and we want to basically pilot a little bit and prototype and see and test out what possibilities we can have based on the data we have. So we go into the system, which you can see now in front of you, and we will be going into it, and we have to, first of all, like in every pilot, create the basis on which this project will run in the end, right? And this basis is a model of the world we're trying to work in. The world we're trying to work in is a wind park. So we go ahead and we create an ontology, which is the base for our worlds. We will create the ontology, and we will go ahead and give it our name. We call it ISGF wind, and this is how our wind parks are called. Now we've already created the basis, and on this basis now we can start in drawing up the things we own and the things we want to measure and the things we see in our physical world, in this wind park world. Now we know we have a couple wind turbines, and we know that in these wind turbines we have lots of sensors and lots of data coming out of it. Specifically, we know that we have in one wind turbine, in one of the wind parks, we know we have an observation that measures the wind, speed. So we put that in. We say that we have a wind speed observation that is coming from this specific one wind turbine in whatever part. And we also know that we have at this exact same location another measurement that is the output power of this wind turbine. Now this will be basically already the data model we have for one specific wind turbine. We know we have the wind speed as well as the output of this wind turbine. But as this is still quite unorganized and we also know more things about it, we can put these things into the system. We know, for example, that both observations are being measured by a specific sensor device in the turbines. Now the sensor device, we can actually go ahead and identify it with an image if we want to, so we have later on better visibility. So we have a sensor, and we can say that, as you mentioned, it's observing these two things. So we can go ahead and we can just tell him that. So we have a first level of hierarchy already in our model that we just created now. And we can go ahead and drive this even further and going up a couple levels until we end up at our wind park. So we'll go through a physical part, which is the wind turbine the things are in. And we know these two are composing each other. Let's go the other way around. We know that the wind turbine one is containing the sensor. So we can mark this here as well, and we have another hierarchical relationship created. The same is true also, obviously, for the wind park we're working in, which is a wind park standing in Frankfurt. So we'll name it accordingly. And again, we can compose these two together with a relationship. And we already have our first full model of our partial world. We already have modeled one specific wind turbine and its measured observations. Now this helps us maybe to document the system if we want to, but we wanted to go further, right? We wanted to see some data coming in. We wanted to also then maybe work with this data in order to gain more insight on things. So we can go back and we can go to the overview of the system. We can look at these things, and we can basically click on the information and see what's happening. But we want to get data, right? So we can go ahead and we say connect, which we can here. Thing we could first of all delete this, and we can go ahead and we can say connected to a data source that we have where our wind turbine data is being saved in. We create a new template, which is for now completely empty. We can name it. We know that we have a database for the wind park in Frankfurt that contains several different tables for the several different wind turbines we're having, and also for environmental data. Unfortunately, this is a quite old database, which here actually is luckily, so we can basically only ping it every couple of seconds in order to get new data. We know it's a Microsoft SQL database. We want to receive new data every 5 seconds, we say for now. It's located locally in my computer. We give it the username to read the data and password. And it's connecting, and as soon as it's connected, we can go ahead and specifically create a connection from the database tables to our ontologic system that we just modeled. So we go ahead and select where we want to go. It's the ISGF wind ontology that we created. This is the world we are modeling. And we have here the wind speed, for example, as one of the observations. We know that the database has a table called data, which contains environmental information, and we know it has also a column that is called wind speed, meters per second. And yes, it's meters per second. So after giving that a unit as well, we still have to identify the timestamp at which this measurement has been taken. Luckily, the database has been constructed that it's contains aggregated data, which each row also containing a column row timestamp, which identifies when the measurement has been taken. Equivalently, we will do the same for the second observation, the output, which this time lies in 3T1 data, and in the column output kilowatts. And here we select kilowatts, and again the row timestamp column in order to identify. Now we've already created the first data connection to any data system we already had where our data is being saved. We go ahead, we see, okay, an overview, a quick overview. 2 connections are being made. We can activate the stream to the UI, and as soon as we go back into the overview of our system, which now we have the wrong selected, so we go to our ISGF wind farm again. And as soon as we hear in the overview, we wait a couple seconds and we see that now already in our nodes, we're having information being displayed unread, which is the real-time data stream that is coming in from our database. Now that's not nearly as informative as maybe a chart, so we can go ahead and see on the side the historic trend of the last couple minutes, as well as for the wind speed if we want to. And we can now see and think that maybe actually these 2 graphs could have something in common. So why don't we just go ahead and for now and see whether these 2 guys are correlated or not. We know that correlation kind of gives an indicator of how 2 things are combined, so we're just going to go and deploy a correlation algorithm to this. Now for that we can either go here and shortcut, excuse me, okay, this was apparently, no, it's got some hiccup. Anyways, so we can either use here the shortcut or we go through another view where we can already see all deployed algorithms, but for now we're going to use the shortcut, which is the correlation algorithm here. Excuse me, no, now there we go. So we go ahead and we wanted to create a correlation algorithm that gives us an indicator of whether those 2 guys, the wind speed and the output, are connected. So we'll name it accordingly so we can identify it later again. We say this is a Pearson correlation algorithm, and we decide for our ISGF wind farm. Now we have a couple of parameters, not a lot, but one here is, for example, the batch size. We say it should, every new observation that's coming in, it should basically analyze again and recalculate its indicators. And we say it should only look back 5,000 observations. We will connect the 2 observations we have identified in our system, and we're scoping this obviously again with our ISGF wind farm ontology, and that's it. We can already deploy this, and it will start running its correlation analysis, and it will start gathering the data and supplying it also to the UI. So as soon as we're back in the system, in the overview of our system, We can wait a second again until the real-time data stream kicks in. We can go ahead now and we will see there's a column statistics in our sidebar menu, which we can open up. And we already see that there's a correlation indication between wind speed and output, the exact two things that we have tried to correlate with each other. And if we look at the historic data here, and we see again the trends, and we see that they might actually have something in common, and this might actually be true. So we can think about now and say, well, this correlation seems to be a good indicator of whether our wind parks, wind turbines are functioning properly or not. If the correlation is low, then there might be something wrong. So let's do this with every wind turbine we have in Frankfurt, and we can go in later and check that everything's working properly. So we can go back to the editor in order to scale up our model, and in order to go ahead and deploy this to every wind turbine we have, for example, in Frankfurt. For that, we simply just select our wind turbine, and we, as the point in hierarchy which we want to replicate, duplicate it by full hierarchy, attach it to the same wind park in this sense, give it the same analytics, and even nicely also increment the numbers and the labels, which now comes why I named these things so strangely. So as soon as we're duplicating them, they should be appearing here. Excuse me, again, some hiccup. Now anyways, after they've been duplicated, one thing that one could do is, as the whole system will become quite confusing with many nodes, one can go into a schematic kind of view and or geographic kind of view, where one can then map and see, replace the positions of the physical entities in order for later on giving the staff, for example, the field crews, a point of entry in which they can also organize the way of work. Now we'll have to stop the demo here in order to not go too deep and go ahead and model the whole world by tonight. And we're going to go back to the presentation now and think a little bit more about where the problem is coming from and what the problem actually is. So let's look at it first from a different perspective. Let's go ahead and think about, well, how does a business usually approach an analytics solution? Well, a business usually goes ahead and identifies a problem and identifies that it has enough data in order to maybe overcome this problem. So the business goes out and creates an internal team or buys a team at a consultancy that is composed usually of data scientists that know their way around the data and that are able to come up with a solution. Now that team will go ahead and talk to all the data and domain experts in the business in order to find the necessary information, the relations, the data sources, etc., etc. After that, the team will gather together and come up with a solution that it can then deliver to the business for it to use it. Now, apart from that solution, typically being really black boxish and nobody really can trace where the results are coming from or why specific input returns in specific output, there's a lot more profound and a lot deeper problem at an even earlier stage of the whole process. Remember that I said that the data scientists have to talk to the domain experts? It's the same as if an English-speaking person is going out and trying to communicate with a Chinese-speaking person by only using Google Translate. Now it works, but not really. There's certain kinds of information that are broken down into just the specific words, and a lot of information is just missing at the other end. What happens is that the domain experts, with all their physical knowledge and all their technical experience in their field, they build a language that is 100% accurate to describe the world they live in, this physical world they live in. Now the data scientists, on the other hand, did the exact same thing, but for a different world. They live in a world that is more abstract, that is made of scientific formulations and mathematics and models. So when these two groups are trying to communicate with each other, both groups have to boil down the level of language they are using in order for making themselves understood. And that change might just be really subtle, but it's enough for creating, in the long term, quite the difficult problems to handle in the end, as it can result in false, tailored solutions. it can result in falsely understood results. It can be basically then also end up in the fragmentation of the different approaches being used, because no one solution is convincing enough for one domain expert in order for it to be accepted 100%. So this slowdown of adoption and innovation is exactly what NetLume is working against by providing one exact same language for every party involved. Now about that language, my colleague will talk a little bit, as he always gets really excited about this technology stuff, and we'll speak a bit more about the specifics of NetLume and its business and technology background.
Okay, so hi from me now too. I can speak now too. Paul, you already did a nice introduction of me, so I will start right into the matter. And yeah, I will get back a little bit to the demo. There you saw that basically even a non-data scientist can start modeling the system and according to their own problem domain and business basically. So as you are the experts in your world, you can incorporate your own knowledge into that model. What you didn't saw, on the other hand, was that what you actually built there was a machine-readable model within a formal framework, so to say. So even data scientists and machines can work with it. And this has quite a serious implication, because it enables you all together, and this is what Paul mentioned with the language gap, you all together can speak the same language and discuss what you draw there in the model, yeah, communicate it and share your knowledge on a quite intuitive and the same level. Now, at the same time, as mentioned, the model is already understood by machines, and this is why you can easily incorporate, for instance, the correlation analytics that you saw in the demo. And in the same way, you can also incorporate other stuff like machine learning algorithms that predict certain variables, or anomaly detection, or just monitor your system with a condition monitoring approach. So now what this boils down is it enables basically a business or a company to be part of a data innovation process again, because you can actively go into the model and incorporate your own knowledge and harvest basically the potential of the data flow that you see day in, day out. Now, on another note, what I personally like very much is while often machine learning and predictive maintenance and all that buzzwords with big data involved, well, you have a black box and you just need to use that black box. But most of the time, only data scientists can use that black box. And with that approach, you kind of crack up a little bit the black box and make the results that you get there, even the analytic results, more traceable and transparent. Now, why is that possible, what we are currently doing with our approach? And this is basically based on the framework that we are using, which is a formal framework that you will see in the semantic web area, and it's called ontologies. So our whole system is ontology based, which means it's a very general formal model of human and machine readable formalization, and you can basically model anything with it. So in this sense, we completely modeled everything with ontologies, from the architecture, from the technical architecture, over to the data model that you saw in the demo, and right into the analytics that you saw there. Everything is in our system is ontologies, and this is why you can communicate with them. Now, what we are currently developing here is not just a product that you can just go out into it, pull out into the world, but we are further developing something like a systematic process which we coined the ACA approach. So ACA in this sense means edit, connect, and analyze, and it's actually that simple as it sounds. So we do not require any form of a big or holistic model of the whole system, but we can establish rather complex systems in a piece-by-piece-wise manner. So you edit a small part. This is what you've done in the demo, for instance. you connect your small system first to some external data sources, and then you can start analyzing the data stream. And this was in a very simple a model done in the demo within only 10 minutes or 15 minutes. And I think it shows quite the power of this approach. So from a development perspective, this whole process increases the agility and adoption rate of analytic solutions by giving you the possibility to quite quickly and effortless prototype an initial system. And moreover, as soon as you have your initial system and you see that it works, you can expand it with the same mechanism. You can just add more nodes, duplicate nodes, and the whole hierarchy, and build quite a complex predictive analytics system, for instance, or just a monitoring system. Now, in the next slide, how does actually our implementation of the process looks like? We have three concepts. The first part is the ontological conceptualization. You saw that in the I explained it in the previous slide, where you have the left pane, the semantic parsing basically. So you have raw data from external sources like an SAP database, Hadoop, MS SQL, or Predix from GE, which is a industrial Internet of Things platform for analytics. Anything that has an API, we can basically connect with parsing comps to them and pull them into the semantic framework. You did this in the demo by mapping, for instance, in the connection phase, the database columns with the observations that you created. Now, in the middle part, as soon as we have everything in our environment, we have the actual Hive system. This is the semantic environment of our stack, and it's centered around the so-called Hive data bus, which contains all the information flow, like real-time sensor streams, analytic statistic results, and history gathering. So everything is in our case, on one central entity, and analytic comps for statistics or machine learning are connected to it and can listen basically to the bus to get the information they need from. And moreover, we already implemented artificial intelligence instances that, for instance, look at the data bus here in it and infer additional information from what it's seeing there and put them again onto the data bus, and other entities can again collect that new information. And we even have a chatbot that is where you can communicate with our Hive in the most natural way for a human, which is natural language. So we can basically speak with our system, and based on the ontology and information flow, it can answer questions. Now, the third part is the view, and this is what you saw in the demo, and you worked with it in the demo, and it actually is just a window into our Hive system. So what you see there are actually the connections that are present in the Hive data bus from the previous. It's also connected like an analytics comp or like an artificial intelligence. It's just connected to the data bus and visualizes the results. So it's basically a visual representation of our Hive backend. Now, I think that should be it from the technical perspective. Now, I hope I make clear that our system is quite big and complex and have therefore a lot of different aspects that you can incorporate there. You can easily scale it up. You can easily add analytic comps as soon as if you want specific stuff. And yeah, Paul will tell you then more about its applications that currently reside, where its applications reside. At least for our case, we see new applications basically every day, and what specific opportunities it can create at least.
Yeah, so but before we can talk about exactly what we can do with it, let's remind ourselves quickly where NetLume has been born into. NetLume has been born into the world of Industry 4.0, or the industrial Internet of Things, if you want, which, if we go quickly over it, is characterized by three key points. The first is that there is a huge amount of data coming from any corner of the whole system. being it sensors, actuators, devices, connectors, or even humans adding more data. So this huge amount of data is providing a basis for changing this processes of a business as it has been working for the last years. And changing in the sense it can be improved upon, can be speeded up, or for example, can be made more automated, or can be run more effectively, or even just a prediction can be made more reliable based on all this data that's coming along. Besides just re-engineering what there has already been there for years, it also gives the possibility to create completely new approaches and new ways of dealing with the problem and the situation. So this huge amount of data also comes along with the potential for innovating and generating growth based on this innovation for the business itself. This potential is obviously not just lying dormant or so, but it's been harvested by lots of different companies with or without the help of consultancies. But what are they actually doing with this? What is the actual innovation behind it? What can be done? And what can be therefore done also with NetLume? If we look at the use cases a little bit and go with the simplest first maybe, we see that real-time monitoring in this instance, for example, is basically the second step of the NetLume's ECA process, right? We were going in, we were editing, and we were documenting our system, our model, and then we went ahead and connected it already to data sources. And after that, we had the real-time data stream. We could then employ some warning mechanisms or rule-based alarm systems, and we would be able to real-time monitor our systems in real time. If we add the A to the process, we end up, for example, with predictive maintenance if we want to. We can go ahead and we can predict when our systems are going to fail, or we can predict when a part needs to be replaced or when a part needs to be repaired in order to increase its life cycle. So these are rather technical parts, but there's also the human kind of part to it. So, for example, you can go ahead and you can create an application on NetLume to optimize your field crew. Here comes again into play the AI assistance that my colleague was already talking about, the chatbot, which will allow field crew members to, without breaking any barriers, talk to the system in order to get the information necessary to execute their orders, being it a plan for maintenance, being it the specific part that needs to be repaired, or even being it a manual on how to repair something. If it's modeled in the ontology, it can be supplied. Now, all these use cases are still really technical. And that's because me and my colleague and the guys here that are sitting at Idatase thinking about these are all quite technical guys. But what we see every day, and what Karl-Heinz already mentioned, is that we get asked tons of questions about use cases, whether it's possible or not. And for example, we had one customer that came along and we did a POC with him that asked whether or not we can go ahead and predict the tender prices for operational reserves in the energy sector. And NetLume delivered. And that basically shows us every day again that NetLume is not just the tool in order to create a list of use cases and to you to be able to use one of these use cases, but it's basically giving you the possibility to think freely again about what you can do with this bunch of data you have and what you can do with the systems you have in combination with intelligent algorithms. If we look at the energy sector specifically, also obviously because Idatase has a long history in it, there's several different vectors that have been coming up and that Idatase noticed throughout all the projects being implemented. It's IoT analytic solutions have to be reliable and they have to be transparent in order for them to become accepted and to become really used in any business. In this hugely interconnected, physically interconnected industry, it's really necessary that if a solution comes along, that it works the way it promises to work, and that there's not just a 70–80% success rate or so. It needs to be top-notch, or it's not going to be implemented. So innovation has to come along with exactly these criteria as well. It has to obey these factors in order to become something that's being used. The couple players that are already going ahead and innovating on a large scale with solutions like that are existing, obviously. But that, in addition with these factors, just pressure everyone else a lot more to create innovative solutions themselves, which is then contributing, in fact, again, to the fragmentation, because people are trying and failing before succeeding a lot. If you look specifically more into smart grids at this point, we notice one thing, that a smart grid is not something that a country or a state goes ahead and wants to implement and then a year later it's going to be implemented everywhere. No, right? It's something that starts small, that grows up in a city, goes from the city to the region, and goes from the region maybe to the state. This piece-by-piece adoption is also what Karl-Heinz already mentioned, how NetLume works at its core if used from a bottom-up approach. It's this piece-by-piece implementation and then expansion to bigger areas and to larger systems as a whole. Smart grids, on the other hand, as well, obviously are the classic IoT environment. There's a lot of different sensors, actuators, things to monitor, things to observe, things to interact with, and humans putting in data, humans taking out data, etc., lots of automations. Now, the typical use cases come obviously to mind here, like predictive maintenance, grid anomaly detection or reactions, real-time monitoring, or even emergency monitoring or reacting. But what does it come all down to, right? Let's go quickly again through the 4 steps that we've been talking about here and that are really important in order to grasp the scale of this solution. Now, the problem is that the different groups and businesses have a language evolved from different backgrounds, and this language gap between them makes it hard for them to get on the same level and to speak in an accurate way with each other. And that in turn results then in a slowdown of innovation in analytic solutions and in the adoption of analytic solutions, and obviously then also as a result in the fragmentation of the approaches, specifically also in IoT. NetLume solves that. NetLume gives one tool to speak with everyone. It eliminates this language gap while also streamlining data sources and the teams working with it. In combination with the Idatase ECA, if you're not going holistic and you're not going from top down, but you're going bottom up, you can speed up the process. Your analytic solutions are being created and your analytic solutions are being adopted. So it's enabling back again an agile process in a very static environment. And the 4th point that my colleague spoke a lot about is the technology part of it, which the ontologies and specifically this semantic web standard is a state-of-the-art concept that is whose future adoption is to be expected. And as it's a growing field, and the IoT is also still a growing field, is the one key component that's been used in lots of different places. So its future is to be expected. Now, at this point, we will end our presentation and we will answer any questions you have posted through the chat or are posting now through the chat. So please go ahead and send us any questions you have. There seems to not be coming any questions through yet. Please go ahead and send your questions if you have any. Otherwise, we will quickly go a little bit more into the details of exactly this ECA approach that we're giving along with NetLume, or that we're recommending to use as well with NetLume. So, if we look at it from a more specific and particular point of view, also again in combination with NetLume, we see that these 3 steps are a bottom-up approach, right? It's you go into the system, and you don't necessarily need to know already where it's going, but you go ahead and you start off by piloting. That's the whole idea. You're starting off by piloting small parts of the system in the editing phase. So what you do is you go ahead and you create from the smallest possible portion of your system one instance. You create the observations as we've seen in the demo, you create the sensors, and you create the physical parts in which they are contained. Now, after you've done that, you basically already have documented the physical system and the physical world you're living in. So this is already a basis on which everything can work. Like any component, be it a human or being it a machine, can consult this documentation in order to work. And that's exactly what NetLume then does. It goes ahead and it connects data sources to exactly this kind of framework. And the data sources, they know where to look because you have documented the system in a way that the machines as well as the humans can speak. So after you've connected then the data sources, the analytic parts, which are nothing else but another kind of data source, they can go into the ontology again, into the base of the system, in order to extract the information that has been put off another of these data sources, which is actually reading data and putting it in. So these different combos that are working on the ontology are using the ontology in order to speak with each other and to understand what the other person or the other combo is talking about. And the human in this part is doing exactly the same, except for that we're able to visualize it nicely for the human in order to have not a crazy XML file or something like that, but you have a nice graph that can be looked at, that can be understood with one view, or you can have it as a physical view, or you can have it as a schematic kind of blueprint layout, and you can already see parts how they're working with each other. So in the end, you'll be able to visualize everything based on this ontology without compromising the level of in-depth documentation that can be used by machines and algorithms. Now, as we still haven't received any more questions, we're again giving you the chance, we still have some time. Please, if you have any questions, send them to us now. Otherwise, we will be ending this presentation now. All right, so now we have some questions. I just have to wait a second until they pop up on my screen, the questions, then we can go ahead and answer everything. Now the question is, how do you think you differentiate from big players such as GE and Predix? Now, we're not differentiating in the sense that we're trying to compete. The idea behind this is that the analytic comps that are being used can be something that Idatase wrote, can be something that you as a user of the system write, or it can be third-party algorithms such as Predix or other libraries or other services that offer analytic services. So in the end, what you can go ahead is you can have NetLume and you can integrate with Predix. And GE is obviously Predix. So you can integrate these systems, also, for example, SAP competitors in that regard, you can integrate their analytic solutions into NetLume and supply them based on the ontology again, and supply them the ontology based on these products again. So you're not bound to a specific set of analytics that Idatase provides you or that you create. No, it's really at its tool set in which you can integrate all the different comms that you can imagine, and these can be Idatase, self-written, or by, for example, Predictive.
It's something like an overlay to the system. So we bridge the language gap of the technical part to the more human part, I would say.
Okay, we have another question. 1 second. Now, we have, as I'm quickly going to read it because my colleague Karl-Heinz can't see the questions. As you said, you have successfully determined the operating reserves. Is it for the whole grid or driven by some local regulation for some particular unit? So the operational reserve prediction, the tender prediction, was a pilot in Germany where it was basically found to. We were helping the customer in order to get better at their tender bids. So that was a local area only, obviously. So where the customer was operating, they were having these operational reserve bids, and they were trying to improve these bids based on predictions, and that's the frame in which it was developed. Now, what does the hexagon indicate? The hexagon indicates the structure of our system. It's called the hive, as we said, and the hive is a comb-like structure. So each of the comms is part of the hive, and the comms can be arranged against each other as much as you like. That's the idea behind it. Now, is there connectivity? Another question is there connectivity over the internet or local net? Well, this really just depends on how the whole system will be implemented later on. And it can be obviously either be a cloud-based solution, so it would be hosted somewhere and you will access it through the cloud, or it's going to be installed on-premise. And then it depends on how the connections can be made and what templates are available for the specific connections. Now it says here also another question is, can it only be used for energy, or do you have other use cases? Now energy is a good example because it's a very sensor heavy and very actuator heavy industry, but it's really not focused on energy at all. It's been growing up there because it's what Idatase has also had lots of experience, and the value was right there. But it can be used in, for example, automotive sector and the transportation sector. We're already having POCs with public transport systems. It's really through this ontology you can model anything you'd like, and thus it's able to monitor or analyze based on everything you would like it to monitor. So there's no specific area it's tailored towards. It's basically the way you model that decides on whether you can use it. Now, another question, is NetLume open source? I think I'll have to answer that with a no for now. Maybe in the future we can make parts of open source, but at the moment, actually not. Another question we have is, can we have more information on how the Hive data bus works? Karl-Heinz, would you like to take some answer there?
So wait, I will quickly have to. Well, can you go to the slide, to the architecture slide? Yeah, exactly here. So to be honest, the data bus is the single point of failure in this case, because if it goes down, everything goes down. But this is kind of intended, at least from our side, a little bit too, because it's the most focused thing that we have in our system, so to say. So you can see it as a big highway lane where all the semantic information is flowing in and flowing out. And it's based on subscription. This is a publication subscription-based architecture. So if you, for instance, want to develop your own comp, analytic comp or something to do, or like a front end that connects to it, you just have to subscribe to certain URIs. That's what they call it in the semantics sense, and then you receive the data bus routes them towards your application. For learning algorithms, this can be for instance, historic values. So you pull a request on the data bus, like in SparkQL, and then retrieve the data bus answers, routes that request to a service that can answer that, and then gives you the answer back. And then you can push the results onto the Hive data bus again, and anyone that is listening or is interested in the specific results or in the general analytic results, they get the information too. So I think the best way to imagine it is a big highway of data which is flowing through the data bus.
So then we have some other questions here. We had one, if we have a SCADA software and we want to be able to integrate it into the railway segment, what is the connectivity that you provide? Assuming that by connectivity, we're speaking about the connectivity to the hardware and to the sensors and actuators, that we do not do in-house, but that will be the job of a partner, for example. We already have long-term relationships there with people who can take care of that. NetLume bases off and starts integrating as soon as there's already a data made available somewhere. So as soon as these the railway sensors and actuators and such have been connected to a data system, they can be exploited with NetLume. Another question? Yeah?
Very quickly to this, it's you can think of it too as some sort of microservices. So the communication on the architecture level is based on a local network and REST APIs. So you are not fixed to implement everything in one language. You can, for instance, put your service in Java or C++ or Python or Scala, as you mentioned. Just need to communicate, to be able to communicate through a REST API.
Another question, maybe rather technical, you want to answer, Karl-Heinz. Is it capable of edge computing?
In one sense. So you saw that for one point, if the obviously edge computing means that you have to be low on resources when you want to try to compute it, for instance, on a smartphone or at some low resource device which is working on the edge. So if your ontology is small, you can obviously do that. What we are currently trying to do and on which we are working is actually edge computing, in the sense that we have some sort of an AI, again, that listens to requests of compiling a structure from the Hive into some form that has low resource capabilities, and you can use it on the edge device. So this is something that we are working on, and obviously we think that we can do it, to answer the question specifically. We are not yet there, but this is what we are currently working on, besides other projects.
So another question regarding if there is no pre-existing data, how does the system analyze? Now that's connected again to the answer we gave 2 minutes before. As NetLume starts exploiting as soon as there's a data source, and without an existing data source, they won't be able to establish a data stream that can then be consumed by the comms and the analytics or the monitoring system. So in that case,
so analytics, analytics that are based on history, obviously like machine learning algorithms, they need data in some form. So you will have to provide the data, for instance, by putting it into the database of the Hive and then connect to it. And then you can issue requests to get the history. But of course, there are analytics that don't really require data, like simple statistics, mean and deviations. And as soon as you get data that somehow deviates from a mean for a certain threshold, you have anomaly detection, for instance, and then yeah. So you can, if you have data, you can put it in. If you don't have data, you can still put some simple basic analytics onto it.
Yeah. And also regarding the data, another question is whether the data is stored on the cloud or a local server. Well, as my colleague already mentioned, this whole thing is built in the sense that every part is a microservice and working on its own. And each of these microservices can be deployed wherever they are, as long as they're reachable through REST APIs. And so there's basically one of these microservices that is taking care of a persistence layer on the Hive level. So the data will be stored in an ontologic format in one of these microservices databases. Now another question, we have operations data in the real-time database and want to understand how to pass the data on for analysis. Now that depends obviously on, I mean, if this question, I assume it's about whether or not, or how you would be integrating this data source into the NetLume's data stream. We would go ahead by determining its structure depending on what kind of real-time database it is, and based on the structure, we would use predefined interfaces that NetLume already has, or we would go ahead and have to create another integration layer in order to, if it's a very specialized system, then it needs to be a specialized integration layer, obviously, in order to get the data on into the dbus, and then it's available like everything else for analysis.
What we did, for instance, in Predix, actually, so Predix has, from GE, has some data asset management and data storage management tools, but we could easily get them through the interfacing. So you are not bound to use some very specific stuff. You can go rather general, and what we don't have, we can basically, we're happy to integrate it as we get a broader functionality from that.
Yeah, and unfortunately our time's up now. We'll gather the questions we still have left, and we will answer all these questions later on through an email, through a follow-up. So thank you again for everyone being here and listening to the presentation. And
yeah, if you have further questions or anything, we're happy if you write just to our email address, and we are happy to answer more questions.
As well, of course.
Thank you very much.
Thanks.